Yes, in today's class we are going to see the graph traversal techniques. Okay, so what is this traversal techniques is, in a given graph, how we are going to visit the nodes. Traversing is nothing but, suppose you take any root node, say for example you take 4. So from 4, which node you are going to visit next? So from, suppose you have 3 and 2, which is 3, 2 and 6, which is adjacent to 4. So 3 is adjacent to 4, 2 is adjacent to 4 and 6 is adjacent to 4. So which is the next node which you are going to visit? So suppose you choose 2. So next we have to see what are all the adjacent elements of 2 and next which node you are going to visit. Likewise, how we are going to traverse in a graph visiting all the vertices. So those things are called as graph traversal techniques. Okay, so we have two methods of traversal. One is your breadth first search, which you call it as a BFS, and next you call depth first search, which is otherwise known as DFS. Okay, so this BFS is a level order search. You call it to be a BFS is level order. Okay, and DFS is going to be the depth. Alright, so first we will see how we are going to solve the BFS. If suppose you get a question like this, find the BFS of a given graph. Alright, so in a given graph, if they don't give which is going to be the root node, you can as well as select any node of your choice to be the root node. Either you can take 0 or 1 or 5 or 6 or 2 or 3 or 4. From that particular root node, you start your traversal. Alright, suppose in a question they give find the DFS or BFS with a root node to be 1, with a root node to be 2. So from that particular vertex, you have to start your traversal. So this is the first condition which we have to note. So in this particular problem, I am taking generally default to be 0. Okay, because I am not going to specifically choose which is going to be the root node. Say for example, I am specifically choosing 0 to be my root node. So how am I going to perform the breadth first search? We will see first. Okay, so this breadth first search can be implemented using the queue data structure. Okay, so queue data structure. So you know how a queue actually works. Alright, it uses first in first out logic. Okay, FIFO, first in first out logic. So alright, so since our root, I am choosing 0 to be my root, so from 0 I am going to start with my traversal. So you have to first check the adjacent elements of 0. So for 0, the adjacent elements are going to be 1 and 3. Okay, because 0 it has an edge to 1 and 0 it has edge to 3. So first in our queue we are inserting 0 being our root element. Next we can choose, either you can choose 1 or either you can choose 3. Anything is fine. Okay, but you have to take all the adjacent nodes of 0, which is our root node. So for example, I am choosing 1. So I can write it as 1 and 3, because for the element 0, 1 and 3 is the adjacent elements. You can write it either way. You can write it as even 3 and 1. No issues. Okay, so how our result is going to be? So first we have visited the root. So you can write 0. Alright. Next you have 1, which is adjacent element. Either it can be 3 or 1 or 1 or 3. Doesn't matter. So here in our problem I have taken 1. So we have to see, we have to go to 1. So this our node is visited, I have given in the result. So next are in the queue I have 1. So I'm moving to 1. Now I'm checking. So now I'm checking for all the adjacent elements of vertex 1. So 1 is here. So for 1, which are all the adjacent elements? You have 0, you have 3, you have 2, you have 5, you have 6. So for 1, you have 0, 3, 2, 5 and 6. So these are all the adjacent vertices of 1. So how you have to insert an element in the queue is, you have to take the adjacent nodes which you haven't visited earlier or which is not in the queue. You haven't visited earlier, or that particular node should not be there in the queue. So for 0, 1 is an adjacent element, but 0 is an adjacent element, but 0 you have already visited. So we are not going to insert in the queue. It is already given in the result. You have already visited and put it in the result. Next, 3. 3 was previously adjacent to 0, which is already, the list is already there in the queue. 3 is already there in the queue. So you should not insert 3. Next you check for 2. It is not visited as well as it is not previously in the queue. So you can write 2 here. Next, 5. 5 is also not visited. So you can insert 5. Next you can insert 6, which is not visited and it is not in the queue. So you can insert it in the queue. Alright. So our 1 has been visited. So you can put 1 in the result. Next you move to 3. If you come to 3, you have to check for the adjacent element. What are all the adjacent elements? It is 0, 1, 2 and 4. Okay. These are the adjacent elements. So what is the next condition which you have to check? You have to insert in the queue the nodes which are not visited or which are not previously inserted in the queue. So for 3, you first check 0. 0 has already been visited. You check 1. It is already been visited. Next you check for 2. 2 is already inserted in the queue. Okay. Next you have only 4. So 4 is not there in the queue and it is not previously visited. So you can insert 4 here. Alright, we have visited 3. We have checked for the adjacent element. So you can put 3 in the result. So next you move to 2. Next you are going for 2. You are checking for the adjacent elements, which is going to be 1, 3, 4 and 5. These are the adjacent elements of 2. Okay. So in the same way, you have to insert the vertex which has not been previously inserted in the queue. So you check for 1, it is already visited. You check for 3, which is already visited. You check for 4, it is already there in the queue. You need not insert it again. You check for 5, that is also in the queue. Okay. So now you have visited 2. We are bringing out of the queue. Next you go for 5. You go for 5. You check for the adjacent elements. What are all the adjacent elements? It is 1 and 2. Okay. What is 1 and 2? 1 has already been visited. 2 is also visited. So you need not do anything to the 5. You simply dequeue the 5 from the queue and bring it out to the result. Next you move on to 6. Which are all the adjacent elements? 1 and 4. Alright. So 1 is also already visited and 4 is already there in the queue. So you can bring 6 out. So next only 4 is there. You check for the adjacent elements. So 3, 2 and 6. 3 has already been visited, 2 is also visited and 6 is also visited. You simply dequeue that and put it here. So this is the ordering of your breadth first search. So you have to traverse like 0, 0 to 1, 1 to 3, 3 to 2, 2 to 5 and next you are visiting 6 and 4. So this is your DFS. But this is not the only result which you are going to obtain. The results can even differ. See, for example, I said either you can insert 1 or 3 here. Suppose in the queue you have inserted 3 and then 1. So what would have happened here? Next, from 3 you are going to visit. So here we will have 0, 3, 1. The results may vary. Okay, as how you are going to choose your root node and the adjacent elements, the result may vary. This is one of the result of BFS for this particular graph. If suppose I choose 4 to be my root element, so initially 4 would have been here. Okay, and adjacent elements of 4 are 3 and 2. So 4, 3 and 2 would have been here. So that is one result. So it is not necessary that BFS is going to have only one particular sequence of number or sequence of traversal. It can have n number of sequence and traversal depending on the choosing of vertex in a particular graph. Okay, so this is your BFS. This is how you have to solve your BFS. Alright, so next we will move to DFS. I will take the same example and we will perform the DFS here. Okay. Okay, the same example I have taken. Now we will see how we are solving the DFS problem. DFS is what? Depth first search. Okay, so you are going to go for the depth and search. How we are going to do a traversal. Alright, in this you don't know which is actually the root node. Okay, how the depth is going to be. So here also you will have n number of results. So how you choose a root node depends. Alright, that matters for getting your result. So it can be any node which you are choosing as a root node. Here also it doesn't, we don't have any restriction that only this particular node has to be a root node. Okay, depending on the problem, if I tell do a traversal from 3. So from 3 how you are going to do a DFS or a BFS traversal, you have to solve the problem. Okay, so in BFS we used queue data structure for getting our result. In DFS you are going to use stack data structure. Alright, so in your stack, what are the operations we perform in our stack? You are using push and pop operation. Alright, so same, I take 0 as my root. I am choosing this as my root. So first initially I am pushing 0 into the stack. Okay, here you can have a result how we are popping out the terms. So you have 0. First you are visiting 0. Right, first we are visiting 0. So you have inserted into the stack. Next, here the condition is you should not write both the adjacent nodes into the stack, or you should not push both the adjacent nodes into the stack. You should choose any one of the adjacent nodes. Either it can be 1, either it can be 3. Since we have taken 0 as our root node, either you can choose 1 or either you can choose 3. Alright, here also I am choosing 1. Okay, so next I am inserting 1. Okay, you have moved. Now this node I have visited. Next I have moved to this particular 1. Now next you have to see for 1 which are all the adjacent nodes. So it can be 3, it can be 2, or it can be 5, because 3 are adjacent. 3 vertices are adjacent. You can choose any one. So for example I am choosing to be 3. Okay, in my case I am choosing it to be 3. So next I am pushing 3. So I have visited 0, 1 and 3. Next I have moved to 3. Now I am checking for which are all the adjacent elements. So I have 1, I have 2, I have 4. Alright, you have to choose any one. 1 has already been visited, so you cannot push 1 back into the stack. So next I am choosing 2, or it should be 4. For example, I am choosing 4 here now. So 4 also I am pushing into the stack. So 3 I have visited. Next I have moved to 4. So 4 I have come here. So what are all the adjacent nodes of 4? It should be 2 or 3 or 6. Alright, it should be 2 or 3 or 6, because all these 3 nodes are adjacent to 4. I am choosing 6. For example, I am choosing 6. So 6 I am moving, I have visited 4, I have moved to 6. Alright. So what are all the adjacent elements of 6? You have 4 and 1. Okay. Whereas 4 has already been visited, and 6, one more adjacent element is 1. So that also we have already visited. So what we have to do from here? We don't have any more nodes that is left unvisited. So when a condition comes like this, when you visit a particular vertex, but all its adjacent vertices are already been visited. So in that case, if you come across a condition like this, then you have to take the method of backtracking. Okay, you have to take the method of backtracking. Backtracking is nothing but moving back to the element which you have previously visited and checking if there are any unvisited nodes, and then you have to go back and search for the elements that are still left unvisited. Alright, so we are staying at 6. Alright, when we are doing a backtracking, we have to simply bring out the elements, that is pop out the elements. So you can put 6 here, pop 6 here. Now you don't have any element in your stack. 6 you have popped out from the stack. So next element where you are going, the next topmost element is going to be your 4. So you are going to do a backtracking from 6 to 4. Alright, now you are checking again for the for adjacent elements of 4 which are still unvisited. So what are the adjacent elements? 6, 2 and 3. Alright, so 3 has already been visited. Okay, 6 has also been visited. Now 2 is only left over. So what you have to do? You are moving to 2. You are pushing 2 into the stack. Now you are pushing 2 into the stack. Now we are visiting 2. Now we are checking if any, you are taking for adjacent elements. So 1 is your adjacent element, 3 is an adjacent element, 4 is an adjacent element, and 5 is also an adjacent element. But 1 is visited, 2, 3 is visited, 4 is visited, 5 is left unvisited. So you have to push 5 into the stack now. Okay, you are pushing 5 into the stack. So after this, you are going to check the adjacent elements of 5. So 1 is there, 2 is there. Only these both are the adjacent elements. 1 is also already visited, 2 is also already visited. When a condition arises from a particular point where no more adjacent elements are left unvisited, in that case what you have to do? Do a backtrack. Okay, do a backtrack. So when you are doing a backtrack, you have to pop out the elements. You are popping out 5. So what is the next element? 2. So you are going back to 2. Going back to 2, what is happening? Again you are checking for the adjacent elements. All the elements are being visited. So you have to pop out 2. You have no more unvisited elements left. So 2 is popped out. Now you have, before 2 you have 4. So from 2 you are moving back to 4. Okay, you are moving back to 4. You are checking if any unvisited nodes are there. We don't have any unvisited nodes. So we are popping out 4. Next, before 4, you have popped out 4. Before 4 you have 3. Now from 4 you are doing a backtracking to 3. You are checking if any unvisited nodes are there. No. You have popped out. You have popped out. Okay, you are just popping out. We have already have this in the list. Okay, so you need not push it in the result because we have already visited these nodes. You are just checking for the condition. You are popping out. You are visiting 3. You don't have any unvisited nodes. Next you have 1. Next you are moving to 1. Again you are checking if any unvisited nodes are there. You have 2, 0, 3 and 5, but all have been visited. Okay, so you are bringing that out. Next you are backtracking to 0. From 3 you move to 1, and from 1 you are moving to 0, and you are checking for any unvisited nodes, but you have already visited everything. So your result will be 0, 1, 3, 4, 6, 5 and 2. So this is one of the result of your DFS. Okay, when you are popping out, if the element are not there in the result which you have already visited, then you need not write it. Just go backtrack, check for any unvisited nodes. If it is visited, again do a backtrack to the previous element in the stack. Okay, if suppose there are any unvisited nodes, then you move to that node, check for the adjacent elements. If any unvisited, push it into the stack. If you don't have unvisited element, you move back you do a backtracking and come back to the previous number which was pushed into the stack. So here how the results will differ. Suppose I am choosing 1 as my root node. In that case, I have 0, 3, 2 and 5 as my adjacent elements. So if I choose suppose 1 as my root element, so my result would start with 1. And next, if I am choosing the element 5 as my adjacent element, any one adjacent element, so my result will start like 1, 5. So this is also one of the result of your depth first search. So did you all understand this concept of BFS and DFS? So these are the 2 graph traversal methods by which we are going to visit the nodes in a particular graph in a particular ordering. Alright, so for BFS, how we are going to implement? Using a queue. You are pushing the first, whichever first element gets in, that element you are popping out in the first, and you are putting it in the result. In DFS, you are using a stack. So you are going on visiting the nodes, you are putting it in the stack. When a condition arises, when there is no more unvisited nodes, okay, then you have to do a backtrack. In that case, you have to pop out the element and move to the previous element which was visited, and from there again you are checking for the same condition. So this is how you will do a BFS and a DFS.